Good evening, everyone. My name is Shannon Eisenhart, and I'm going to be presenting my research on genomic and comparative genomic analysis of two bacteriophage infecting Arthrobacter globiformis. So first off, what is a phage? Boiled down, phages are viruses for bacteria. They'll insert their DNA into the bacteria and use it to reproduce. So the phage have two life cycles. They have the lytic life cycle and the lysogenic life cycle. The lytic life cycle, which is in red, the phage will insert its DNA into the host cell, and that DNA will basically hijack the cell, making it only reproduce phage until that cell gets so full that it will burst out. Whereas in the lysogenic life cycle, that phage will start off the same, put its DNA into the host cell, but then that DNA will actually put its DNA into the host's DNA. Then that phage DNA will end up getting reproduced over and over and over again with the regular, all the other cell DNA. Then what will happen is that for some reason that phage DNA will get turned on. And then that will cause it to take over and start only reproducing phage, which will then make that cell so first that it will burst, restarting that process over again. So there are two groups of phage. We have the temperate phage and the virulent phage. In the temperate phage, they get to choose what cycle they go through, the lysogenic life cycle or the lytic life cycle. Whereas the virulent phage, they're stuck with the lytic life cycle. So why are we doing this research? We don't have a lot of information on phage themselves. We have a very basic amount, but we don't have a lot of the nitty gritty. So as we know, they can do so much for us, but we just don't have that information to put it into effect. So the big one right now that a lot of people are excited about is phage therapy. Basically, if you have an antibiotic-resistant bacteria in you, healthcare professionals can insert phage into you, and the phage will then act as a kind of an antibiotic. But the issue with this right now is we don't have a lot of research on this. It's very new. There's not a whole lot, so it's not that commonly used. So we have to get more research on the phages themselves to be able to then help do more research on other things like the healthcare and the phage therapy. So we were given two phages, Arthrobacter that infected Arthrobacter globiformis, which is a bacteria. We were given ADAM 2043, which was found by Adam Bond, and Prairie, which was found by Brittany Bond in the fall 2019 C phages class. And then we took the information and we were given the DNA. It's DNA, not physically, but basically in a folder, basically. And then we were able to go through and run it through multiple different databases to answer a big question of, is this possible gene a gene? So to do that, we used 4 different databanks. And the first one that we used, databanks and other resources, so the first one we used is DNA Master. Really, DNA Master was the central hub and the stepping stone for the entire project. It can do many, many things. It will allow us to put in genes, take out possible genes, gives us the sequence of that gene, those kinds of things that allow us to go through and get all these other information into the other databanks, into these databanks. So the first databank that we had access to, which phagesdb.org. This contained a lot of the information about the physical phage itself, where it was found, when it was found, who found it, what was its isolation host, those kinds of information, which helps us compare it to other phage found in its little family. And then the third program we used was NCBI Blast Protein Blast. And it's a data bank that allows us to compare 2 DNA sequences or many at once. So I can insert a DNA sequence and it will come back with saying, hey, this DNA sequence is this close, but it has these kinds of errors, those kinds of information, which help us decide on what the function of this gene is and if it actually is a gene. And then the last data bank we used was Famirator. Famirator actually allowed us to physically compare phage. As you can see in the photo here, all that purple means that those genes are exactly the same. They match up. Whereas the white, it means that they're not quite right, those kinds of information. So it allows us to actually see what's similar, what's not similar between phages. So I ended up taking all this information and boiling it down. I condensed it all, and I took all the different genes and put them into 3 categories: structural genes, non-structural genes, and hypothetical genes. So a structural gene is that they make the protein for the phage. They are the building blocks for the entire phage. Whereas the non-structural genes, they do the stuff. As Dr. Amaya says, they're the verbs. They do the jumping, they do that kind of stuff. Whereas the hypothetical genes, we have absolutely no idea what they do. We're lost. So I took that information and I condensed that even more into a pie chart to see what percentage that we had of those genes. So we found that in ADAM 2043, that we only knew what 51%, less than 50% of what the genes did. 51% of the genes were hypothetical. So 26% were structural versus 23% were non-structural. Whereas in Prairie, we knew that 58% were hypothetical, the genes were hypothetical. So that means we know even less about this phage. So like I said, we're doing this research because we know very little about these phage. We know less than 50% about what their genes do. So what can the genes tell us themselves? So they can tell us many things. The big one is they can tell us what kind of phage, and that's what I was looking at, what kind of phage they were. They were able to tell us that ADAM and Prairie are both temperate phage. What that kind of tells us is that we know that they will we know that they can choose what life cycle, excuse me. So ADAM actually replicates differently than Prairie, and we learned that just by looking at its DNA. Prairie will insert its DNA into the host, and it allows itself to actually not get into Prairie will insert its DNA into the host, but it won't actually put its DNA into the host's DNA. Whereas ADAM actually will insert its DNA into the host's DNA. So in Prairie, the phage DNA just kind of hangs out there, and it still gets replicated over and over again. When the cell replicates, it's kind of hanging out there, that it just kind of goes under cover. So it's 2 different mechanisms that they go through to survive. So going forward, there's many things that we can do with this information. The biggest one is that we can do a 1-step growth curve to identify when different genes are turned on. This will allow us to identify what is made when, that kind of information. So that's a big one that we can do. We can also go through and isolate and identify unknown genes and figure out what they do. I don't know a whole lot about this process, and I'm excited to learn more. And lastly, we can actually go back out and go find more phage and start the process all over again. Lastly, I'd like to give special thanks to Dr. Amaya Garcia-Gonzalez, Darian Brown, the CBASE program, the Fall 2019 C-Phages class, and specifically Adam Gilson and Brittany Bond for the use of their phage in my research. Thank you all for watching, and have a good day.